Okay, so welcome to the first lesson of quantitative chemistry. So moving forward, this is going to look very different from what you have previously experienced in chemistry. Now we are going to look at measuring the quantity of the substance in a sample, looking at how much of a product you get, not just what kind of product you get. How can you quantify how good or efficient the reaction was, not unlike percent error, which maybe you have done in physics, and then using that data to then be more accurate and analytical with your experiments. So things like testing levels in the blood. So I'm a type 1 diabetic. I test my blood sugar level often, all day long. I wear a sensor 24/7 that can tell me the concentration of sugar in my blood. So I don't necessarily, yes, I know there's glucose in my blood, but I need to know how much glucose there is. So then I can make adjustments to my insulin, whether I'm going to give myself insulin or have a snack if I'm too low. So I have to make essentially life or death decisions. Indoor and outdoor environments, monitoring gas and other contaminant levels. This is huge. So many of you who choose to continue in science, you may find yourself at this kind of job, and it is, you can work for a corporation. I worked for SC Johnson, and even though they are sort of a warehouse and a factory that makes in Brantford at that time, we made candles mostly. There, I didn't make the candles, I didn't work in the plant. I worked in the lab where we had to assess the quality of the candle and made sure it was up to spec and all that kind of stuff. We had to measure acidity, which is part of what we're going to do in the next unit. Outdoor environments, monitoring contaminants in soil and water, even monitoring what's in the soil and water is important. And that data is often available and you can look it up, and people don't even realize that you can actually, people talk about, oh, this in the water, that in the water, and you can actually, the city, for example, provides data that you can look at and know exactly the amount of whatever substance you're concerned about is in your water. And then sports, monitoring performance enhancing substances, which has a wide variety as well. Okay, so we have represented atoms, molecules, and compounds using different diagrams. So this one here is the one on the far left is a very simple Bohr-Rutherford diagram. This, of course, is a Lewis structure for CO2, the compound. We drew those in the first unit. And then this is just a Lewis dot diagram for carbon. So now, instead of using these kind of drawings, we're going to use numerical data to represent the type and amounts of different atoms, molecules, and compounds. So your textbook is very particular and likes the word entities. So I believe I've talked about this before, but when you have the word molecule, even though we kind of throw that around, it really should only be used to describe a compound that has covalent bonds in it, or a molecular compound or covalent compound. So instead of talking about molecules, your textbook is going to be more correct and using the word entity. So the diagram tells us what type of entity is part of a chemical reaction. But like I said, moving forward, we want to know exactly how much we're using, how much we're producing. That's obviously the next step, much better. Okay, so sorry, I'm going to get rid of this. Molecular weight or molar mass. So each element on the periodic table has an average atomic mass based on the isotopes, which again, we talked about in the first unit. So now we are not going to use the rounded atomic mass. We are going to use this average atomic mass reported on the periodic table because our sample is going to contain the different isotopes in the same weighted isotopic abundance that we calculated in the first unit. So using the average, again, is much more analytical and correct. You can have 0.1 of a gram of a sample, for example, whereas you can't have 0.1 of a proton. So we rounded in order to figure out the number of protons, neutrons, and electrons. So again, a very surface analysis of what's really going on with chemicals. So I'm just gonna introduce molecular weight and a really simple calculation called percent composition. The next lesson, lesson 2, delves much more in depth into what is a quantity that we're going to use, which is called the mole. Okay, so you do need your periodic table. Again, you don't need to memorize it, but it says here, what is the molecular weight of iron metal? So iron metal has the formula Fe. So you go to iron, which is number 26, and on the periodic table in the top right hand corner, if you use our periodic table, says 55.85. So what happens when you have a compound? So again, you need to know the formula, which that's why we reviewed naming this year. So we have one carbon atom, which is 12.01, has an atomic mass of 12.01. Oxygen has 16. So since there is only one carbon, then you only are going to add one carbon, but we have 2 oxygens. If that is awkward there, you maybe want to write oxy so it doesn't look like the number 20. So you have to multiply oxygen's atomic mass by 2 because there are 2 of them. Okay, so let's do the molar mass or molecular weight of magnesium chloride. So again, you need to write the formula. Okay, so you crisscross and you would end up with MgCl2. I will write it like this example here. Moving forward, molar mass or molecular weight is actually going to be one of the simplest calculations that you are going to do. So you will probably in the end only need to write your answer, but for now we'll just show all of our work. Okay, so we're going to use 1 magnesium and 2 chlorines. Magnesium is 24.31, chlorine is 35.45. Which gives us 95.21. Okay, so pretty straightforward. So then when you go to do percent composition, this is a calculation used to determine how much of each type of atom is in a molecule based on mass. So we're going to use either, you can often, more often than not, the question is just going to say find the percent composition of, for example, magnesium chloride, and you're just going to use the molar mass or the atomic mass on the periodic table. Sometimes you can be given actual grams in the question. It actually really doesn't matter. Okay, so when we want to represent the composition or the fraction of the molecule or compound that is made up of each atom, and we're going to express it as a percentage. So in the end, we're going to multiply by 100. Okay, so when the old way of thinking about ratios, let's say you have hydrogen chloride, then you have 1 atom of hydrogen, 1 atom of chlorine, 2 atoms total. So if you were going to represent that as a percentage, then according to what you've done so far, then you would say, oh, well, 50% of the atoms are hydrogen and 50% are chlorine, or 1 out of 2. However, hydrogen or hydrochloric acid or hydrogen chloride, hydrogen has a tiny atomic mass and chlorine has a much larger mass, which means that the chlorine is going to take up a greater percentage by mass in the compound. So it gives a better idea of if you could represent a molecule using circles, then the representation should show chlorine with a much larger atom. Now, this does relate, the mass comes from the number of protons and neutrons. So the more protons, then the bigger the mass is. And we talked all about that in the periodic trends. So yes, chlorine is a bigger atom. So then it is a much better way to represent the composition of hydrogen chloride than just doing the number. So one hydrogen atom out of two total atoms is 50%. It is very clear that it is not going to be, it does not make up 50% of the molecule in any sort of real sense. Okay, so this here is the formula to calculate percent composition. And really, this is, if you think about what a percentage is, like if you're percent on a test, what you got out of the total marks, then this is pretty straightforward. So the percent of an element is the total mass of the element divided by the total mass of the compound times 100. So like I said, you could use mass in grams, or you could use the atomic mass. And that's what it's saying here. If not given actual masses, just use the periodic table and the atomic mass. You will have to write the chemical formula if it's not given to you. And you need to find, if it says, the question simply says, find the percent composition of whatever, then you need to find the percentage of each element separately. The questions generally are not going to say, find the percent magnesium, find the percent chlorine in magnesium chloride. So you do need to know that. Now, most of the time, like if it was, find the percent comp of MgCl2, then that's no big deal. You do percent Mg and percent Cl2, or Cl, sorry. The thing that can trip people up is, what if it's something like this, NaSO4, then you'd want to do percent Na, and this is one instance where we are going to split up the polyatomic ion. So you would find the percent S and the percent O separately, okay? So just be wary of that. Okay, so hydrochloric acid, or HCl, let's look at that. Again, I'm going to show lots of work here, but moving forward, this percent composition, the reason we're doing it on the first day, it is one of the more straightforward calculations. Okay, so when we have, you need the molecular weight of the compound, which in our case is HCl. So you have one hydrogen and one chlorine. Hydrogen is 1.008, chlorine is 35.45. That is on the other slide, but again, that is straight up from your periodic table. If you are using a different version of the periodic table, which is totally fine, you might find that it's rounded a little bit differently. So that's reasonable as well. It doesn't matter. Okay, so when you do the percent hydrogen, it doesn't really matter. You could do hydrogen first or chlorine first. Then you're going to do the molecular weight of hydrogen over the molecular weight of HCl. So a percentage, which is times 100, is always the part over the whole. So how much of our compound is hydrogen represented as a percentage? Oops. .76, which makes sense. It should be a tiny percentage because hydrogen has a tiny mass compared to chlorine. So you can see here, 35.45 out of over 36.458. That's much closer to 1. So this percentage should be much higher. Okay, so their total should be 100. So really, we could have streamlined this. And once we got the percentage of hydrogen, we could have just subtracted from 100 and gotten the same answer. But I wanted to show you a full question. Okay. Okay, and that's perfectly reasonable as well. Okay, so let's do carbon dioxide. So again, you need to write the formula. Okay, so CO2, you need the molecular weight of carbon dioxide. And again, multiplying by 2. Oxygen's molecular weight is 16 right on. I'm just going to keep going here to make sure that I don't run out of room. Okay, so when you do this, don't forget that you need to multiply the molecular weight of oxygen by 2 because there are 2 of them, okay? But again, you could have done 100 minus 27.3 and gotten the same answer. Okay, so the percent composition is a useful calculation because it has to follow the law of definite proportions. So what that means is, let's say you have water in Canada. If it's pure, then it's going to be 2 parts hydrogen to 1 part oxygen. It has to be the same. Elements in a compound are always present in the same proportion by mass. So then if you had water that was, somebody was calling a substance water and they said it was pure and it didn't have the same percent hydrogen, percent oxygen, then you would know that they were not telling the truth. So, or if you, in a forensic sense, if you found an unknown compound, then the percent of each element in the sample could be determined and the identity of that substance could be determined. So usually in that kind of question, then you would have actual gram amounts because sometimes you might not even know what it was and you could go back and figure out what the compound was based on its percent composition. And we'll do more of those questions when we get to empirical and molecular formula. Okay, so given actual data, so we have a 500 milligram tablet of aspirin, contains 300 milligrams of carbon, 8.08 milligrams of hydrogen. The remaining mass is oxygen. Determine the percent composition of aspirin. So really, you could do it with this, and you should get the same answer. So I'm going to use the actual milligram amounts, but if you didn't, you should get the same answer if you use percentages. It says the remaining mass is oxygen, so we do need to figure that out. So if the total is 500, 300 is oxygen, and a little bit is hydrogen. We get 191.92 milligrams. So when you do a percentage, because the units are percent, like the milligrams or the atomic mass units, should cancel out because you've got one on top of the other. It doesn't matter. It doesn't matter what they are as long as they match. So you don't even have to change them into grams or anything like that because they're going to cancel out. So if you have 300 milligrams for carbon, 500 milligrams total, the milligrams cancel out. So that is incidental. It doesn't matter. So you get 60%. I'm just going to do each one again so you can see this over and over again. But like I said, this calculation in the grand scheme of this unit is going to be one of the more straightforward. So I recommend that you do as many of these textbook questions as you can so that you can get the feel for it. So, again, if you did not watch any of the last units, videos, there is an online textbook. Actually, I think I included the link in the announcements as well. Nelson has put the textbook online until June 25th. if you forgot your textbook at school. Okay, so you can also check the logic of your answer. Carbon had the most mass, so it had 60%. Hydrogen only had 8 milligrams, so very little, so a tiny percent. So then since oxygen is 191, that's in between, then it should not be as high as 60, but not as low as 1 either. You could also, check the total. Your total should give you 100. Okay, so we found the percent composition of aspirin, we found the percent carbon, percent hydrogen, and percent oxygen. So pretty straightforward. So like I said, please make sure taking a look at these questions. These are nice, wonderful, easy marks to get. Okay, so I'm working on, they finally have given us the go-ahead for assessments. So I'm going to spend a little bit of time working on a calendar and figuring out what that's going to look like. But I wanted to get this video posted today, as I said I would. So technically, on Monday, you can start looking. I'll post it probably by Friday, and then that'll give you an idea of what next week is looking like. Remembering, even though we can't really go anywhere, Easter is a 4-day weekend, so give yourself that brain break. I'm sure lots of teachers are adding stuff to their D2L pages if they haven't already. Okay, so yeah, look forward to the mole lesson, which is next, which is very exciting.